Brilliant. Welcome back to session 3 of the SOS sessions for fractions. So in the last part 2, we finished up on the vocabulary breakdown. So one area I'd like us to really focus on is this area of proper fractions and improper to mixed numbers. Now as we move in towards upper end of Key Stage 2 and we start having a closer look at calculations in relation to addition, subtraction, multiplication and division. So for example, if you've got children who are not particularly secure with their times table knowledge, I would really sort of consider using this visual here to help them transfer from an improper fraction to a mixed number. Those children who are secure with their times tables will probably pick up how to convert from an improper to a mixed number without really drawing these pictures. So in this case, you've got 7/3. Now, what's really important is that you've got your thirds, and you're aware that that there are 3/3 in a whole one. So you would go through each of them, those 7/3, that's making a whole, and then you've got that one remainder. Therefore, you've got two holes which contain 6/3, and then you've got that one remaining 7th third. So you've got 2 and 1/3. Okay, right, let's move on to this SATs question and have a look and see what you think. Okay, so here we have improper fractions. Circle the improper fraction with the equivalent to 6 and 7/8. So just pause for a moment and either you can draw it or use your times tables. See if you can convert 6 and 7/8 and decide which one of these improper fractions it's equivalent to. Okay, how did you get on? So we've got 6 wholes, and what's really important is this denominator in 8s. So you would do 6 times 8 because there are 8 in each whole, and there's 6 wholes. So that's 48, and then you've got those 7 remaining in the numerator. So 48 plus the 7 would bring us to 55/8. So 55/8 is your answer. Now let's move on to calculating. So most of us have learned the procedures for operating with fractions without really seeing or understanding the mathematical structure that underpins these processes. Doing without understanding can lead to not being able to undo when things go wrong. So it's really important we look at how we can break these processes down and why they work. So let's begin. Now, first of all, let's look at calculation with fractions all the way through Key Stage 2. So at Year 3, they would add and subtract, but they've got the same denominator. So it's something like 3/5 plus 2/5. So it should be very straightforward. Then Year 4, they add and subtract fractions with the same denominator. And then, so they're just continuing on with that a bit more. And then in Year 5, we look at different denominators, and this is where understanding multiples comes in very handy, and hence why doing your times tables test at the end of Year 4 really kind of lays the foundations for picking these concepts up very quickly. And Year 6, you're looking at adding and subtracting, and multiplying fractions, and then dividing as well. So one key thing children need to understand before moving on to these calculations is unitising, and this starts really, really early, even in EYFS. And so it's kind of also in mastery, this notion must that I'm about to show you can be referred to as sort of procedural variation. So if you know that 3 plus 4 equals 7, you could therefore generalise that to 3 apples plus 4 apples equals 7 apples. Or 3 tens plus 4 tens is 7 tens. And then 30 plus 40 plus 70. 3 times 5 plus 4 times 5 plus 7 equals 7 times 5. So all of these facts that you can kind of extrapolate from 3 plus 4 equals 7. 3 tenths plus 4 tenths equals 7 tenths. and therefore 0.3 plus 0.4 equals 0.7. £3 plus £4 equals £7. And 3/8 plus 4/8 equals 7/8. Okay, so unitising helps children to understand adding and subtracting fractions, and why you need to find common denominators. So let's look at this misconception. So often when adding or subtracting fractions, people add or subtraction with both numerators and denominators the same. So if you take a look at this one, okay, and perhaps you've got an idea of how they might have got that 14. So 5/7 plus 1/7, this child's got 6/14. And they've decided that 5/7 take away 1/7 equals 4/0, which seems very plausible, but it's not quite that way, as you know, because we've talked about sevenths in this case. So pupils do not recognise that the denominator indicates the number of parts of the same whole, and therefore treat the two fractions as 4 whole numbers to be added together. Okay, so if you see these sort of misconceptions, I would kind of re-look at some of the part-whole strategies that we talked about in part 1 and 2 to kind of address that. So let's look at the procedure for adding and subtracting fractions. So these first two I'll have a go at with you, and maybe the bottom two you can have a go on your own, just at your leisure. So, for example, so if we've got this one here, we can't really do a quarter. We could have put, if this fraction was larger than a third, then we could just simply put the 1 here and do a quarter, take away a third. However, it's not, so we're going to have to convert that mixed number to an improper fraction. So 4 times 1 is 4, plus that remaining one is 5/4, or 5/4. And then we subtract 1/3. So the trick here is then to find the lowest common multiple, in which case invite the children underneath to list the multiples until you find one in common. Don't get too carried away, because you tend to kind of find a common multiple by the time you get to the 5th number. So even though they know their times tables, you can see them sometimes get a bit carried away writing them out. But already, if they're fluent with a lot of their tables, they should be able to predict. So in this case, a child might routine, if they don't spot it, they would just go down with their routine 4, 8, 12, okay, 3, 6, 9, 12. Okay, so we've got our lowest common multiple. Multiple is a number that is in that times table. So multiples of 4 would be 40, 44, and 4 itself, for example. And obviously multiples of 3 would be 3, 6, 9, 300. These are all multiples. So the lowest one is 12. So the routine here is that if whatever you do to the bottom, the denominator, you've got to do to the top, like we did when we expanded those fractions earlier. So here we're having to get to our lowest common multiple, we're doing 4 multiplied by 3. So therefore this numerator needs to be multiplied by 3. And here we're doing 3 multiplied by 4 to get to 12. In which case our numerator then needs to be multiplied by 4 to find its expanded equivalent. And then it becomes much easier, because you've got 15 over 12 and then you've got 4 over 12. So 15 twelfths take away 4 twelfths becomes much easier, in which case this is 11 12. Okay, as your final answer. Again here with 3/10, so subtract 1/20. Now these below would be exactly the same, however you would add. So the operation would just be to add. All right, so I'll just go through this subtraction example and then you apply exactly the same procedure except you're adding in both cases. All right, so 3/10. Let's count up in those multiples. Right, bingo, we've got it. So 20 and 20 are the lowest common multiple. So here we've got 20, something 20ths, subtract something 20ths. So we've had to multiply by 10 by 2, so we're going to have to multiply 3 by 2, in which case we've got 6. And then we're multiplying by 1 or itself, so we're just sticking with our 1. So 6 over 20, take away 1 over 20, it's 5/20. Okay. Have a go. See how you get on with these two at the bottom. Okay. So just pause for a moment and have a go. Brilliant. Okay, so hopefully you've had a chance to have a go at those last remaining two, and we'll move on to the next slide and looking at multiplication. So revisit the link between multiplication and arrays. So here we've got an example of 2/5 times 3/8. So if we think about how we would demonstrate that as a structure, if we could do that pictorially, what if we had one unit? Let's go back to the arrow. Okay, so, and then we divided it into fifths. And so we've got 5 parts here and 2 are shaded. Okay, and then in the other direction we add our 8s. So we've got 8 parts going in rows and 3 are shaded. So therefore 2/5 multiplied by 3/8 is this overlapping bit. Okay, and so that is 6/48 because you have got, 6/40 because you have now got 40 parts. Because if you're multiplying, you've got 5/5 times 8s, so you're going to end up with 40 parts, and you have got 2 times 3, or you've got those 6 parts that are overlapping. So your answer is 6/40. Okay. So again, let's have a look at it this way. So 3/8. This is a really nice sort of visual way to see why multiplication works. So you've got 3/8, 1, 2, 3, 4, 5, 6, 7, 8, 8 columns, which are parts. And then you've shaded 3, and then you multiply it, so the number by 2/5. 1, 2, 3, 4, 5 parts, and you've shaded those 2 parts. I'm not sure what's happened there with the animation, but there should be 8 times 5, which is 40 parts, and 3 times 2, which is those 6. So you should end up with those 6/40 there. Okay, try these with the image with the arrays that I've just showed you. So you could do that on a gridded whiteboard, or you could just multiply and out your numerators and denominators. But that conceptual way is quite a nice way of seeing why the structures work. So have a go at these last 4. Okay. You just pause. Right, hopefully you've paused and haven't had a little go. And we'll just go through some of the answers. So here we should have 1/12. Here 1/2 times 1/3 should be 1/6. This one, 1/4 times 1/4 should be 1/16, and 1/4 times 2/3 should be 2/12, or you could simplify that to 1/6. Okay, making connections through representation. So multiplying simple pairs of proper fractions, writing the answer in the simplest form. So for example, very much following, so you might have thought those arrays were quite unclear. I mean, why would multiplication have to work like that with those columns and those rows? Let's take sort of smaller fractions. So we've got another unit and we've broken it into quarters. We want to multiply that by a half, or divide it by 2. We'd split it down the middle, like so. And therefore 1/4 times 1/2 is that little bit there that overlaps. So you've got 1/8, because you've got all of these 8s left, but this is the 8th that's left. Try these. Okay, so have a look. So here you can either multiply them by half or divide by 2. You just cut it through the middle. What would it be? What would be your answer? And is there anything you notice? Right, how did you get on? So half divided by 2, or half times a half, would be that quarter. And a third divided by 3, not very equal, but you get the idea, would be a 9th. And a fifth divided by 2 would be 10th. And 2/5 divided by 2 would be 2/10. Okay. So there we have it with the visuals. Let's look at division with going through the procedure. So later on into year 6, the children learn the procedure. As a way to remember it, my children remember keep, kiss, flip, or keep, change, flip. And the whole notion is it's a bit of a magic trick, which is why it's really important that children experience why the concept works initially before they go on to these procedures. So in this case, the whole notion with division is that 8/15 divided by 5/12 is the same. So you're keeping, kissing or changing, and flipping. So it's a funny rule, but it's always those ones that you kind of remember. And then you flip. So it's not 5/12 anymore, it's 12/5. And then because it's multiplication, that's really one of the simplest fractions, because you just multiply the numerator and you just multiply the denominator. So 12 times 8 is 96, as we've got down here, and 15 times 5 is 75. Okay, right, have a go and see if you can do these ones at the top. Right, Joe, just pause for a moment and have a go. So this first one would be 72/21. This one would be it would be 16/55. And this one would be 24/18. Okay, that's your final answer. All right, but you could also simplify some of those should you need to. But sometimes in these tests you don't need to, especially if they're timed. Okay. Right, a few final concepts to note when you're doing these procedures, which sometimes the children can be a bit thrown by. So anything over itself is 1. So one of the previous slides that we looked at, say for example this one. So if we were doing half divided by 2 procedurally, it still works because, so if we did 1/2 divided by 2, now any whole number converted to a fraction is 2 whole ones. Okay, or you could think of a fraction as divide. 2 divided by 1 is 2. So that's why that works. So then if you keep kiss flip, you're doing 1/2, you're keeping that, you're kissing, and then you've got 1/2. Hence why your answer in this case is 1/4, like we said earlier. Okay, so that's, so even with the procedure works that way, or conceptually it works this way. Okay, let's bring it back ahead. So that's one key thing to think about. So 12, oh yes, so that's point number 2, 12 over 1 is 12. So 12 whole ones is 12. And anything over it itself is 1. So obviously 12/12 is 1. It seems quite logical with the visuals here, but you'll be surprised at how many children forget that sometimes. And really kind of understanding that concept helps so much when it comes to things like converting from improper to mixed numbers. Okay, so with those notions in mind and all the procedures that we've talked about in terms of addition and subtraction, finding the common denominator, and multiplication where we multiply the numerator, multiply the denominator, and division where we keep kiss flip and then multiply the numerator and denominator. So all of those different calculation strategies and procedures at our fingertips, and with the concepts that we've just talked about, have a go at this. So we've got a reasoning and problem solving question. This is a typical SATS paper question. The length of a day on Earth is 24 hours. The length of a day on Mercury is 58 and 2/3 times the length of a day on Earth. What is the length of a day on Mercury in hours? Okay, so you're doing 24. So have a go yourself, have a pause, see how you get on with that, and then we'll go through it together. Okay. Right, let's go ahead. Hopefully you've had a chance to pause and write something down. So 24 times 58 and 2/3. So you could tackle this in 2 different ways. You could either convert that into an improper fraction and do that 24 times over 1 and then multiply it out, which would be a massive number. Or you could partition it, so you could do 24 times 58 and 24 times 2/3, a bit like a grid method concept. So I'm going to do the latter, so 58 up here times 24, and then I'm going to add them together at the end. Okay, so this sort of grid idea. Okay, so 8 4s are 32, and 4 5s are 20 plus the 3 is 23. We put the 0, cross that off because we've exchanged. We put the 0 in as a placeholder. 2 8s are 16. Put down the 6, exchange the 1. 2 5s are 10, plus the 1 is 11. So you've got the 11 in there. Okay, and then draw your line, adding them up together because you've multiplied them out. So we've got 2, 9, most tidiest, but you get the idea. 1. Okay, so you've got 1,392, and then I'm going to do 24 4 over 1, because that's the same as 24 multiplied by 2/3, multiplied by 2/3, and that equals 48 over 3. Okay, and then we've got to add those together. So we've got 1,392 and 48/3. Let's put that into a mixed number. So how many 3's in 48? Well, I know there are 3 10s in 30, so there's 18 remainder. But then that means, yes, so that's 10 plus 16. But yes, because 10 3's are 30 and 6 3's are 18, which would make 48. So you've got 16 there. So you've got 1,392 plus 16. Okay. You've got 8, 0, 4. Now I can cross out what I've exchanged. And then I've got the 1 there. Okay. So the length, so I've taken my 24 hours, I've multiplied it by 58, and I've multiplied 24 by 2/3. I partitioned it both, and then I've added them together. And so my total is 1,408 hours. Okay, remember to include the context. Brilliant. Okay, so there's an idea of how you would solve that. But obviously there's lots of different strategies when you're solving a reasoning problem. And here's a mastery question at year 6. So kind of following on from the questions that we've done before. So only a fraction of each whole rod is shown. Using the given information, identify which rod is longer. So if you've got 1/8 and it's that size, and you've got 1/9, which is exactly the same size, which one is longer? So I'll leave you to have a little think about that. So I would say that 1/9 is longer because you've got 9 pieces, and then you've only got 8 pieces there. Okay, so it's going to be longer for 9 because it's 9 of them. And then at greater depth, only a fraction of each whole rod is shown. Given the information, identify which rod is longer. So we've got 2/7 and 3/9. So a little bit of thinking there. Which one do you think would be longer? Now I would say, well, 3/9 is equivalent to 1/3. So you know there's only going to be 3 more of those underneath. Whereas if you've got 2/7, you're going to have 3 more of those to make 6/7, and then a remaining 7th. So this top one must be the longest. So, but you might have other strategies. What do you think? Okay, so that just gives you a bit of an idea about what some of the reasoning questions might look like. But hopefully what we've talked about over these sessions in terms of the concepts behind fractions, it's enabled you to think flexibly and a bit more confidently about some of the questions that you might get throughout the primary curriculum. Okay, and that then leaves me to just finish off with the last of these sessions for fractions. I hope you found it useful, and if you followed part 1, part 2 and part 3, hopefully there's something that you can take away with you to your classrooms and that you found useful. It could be a website, an interactive game, a starter that I've mentioned, or maybe that visual for a particular child that you think might be struggling with some of the concepts behind fractions, or maybe maybe there's a particular resource that we've mentioned that you were prepared to experiment with. So what I'd like you to just cast your mind back over those sessions. Can you pick up 3 actions that you intend to take with you over these sessions, over these parts that we've gone through in relation to fractions? And the very best of luck. Always like to hear how it's going. So if you have any questions, or if there's something that happens that's really positive, or anything you want to mention in terms of what we've been discussing today, please contact me at kandrews@sfet.org.uk. Thank you.